chapter 16, as we finished up, I believe 15 last time. So 16 seems like a good spot. So we're going to change gears a little bit, and we're going to talk about in this chapter some thermodynamics, and we will tie together some new letters, entropy, which is delta S, free energy, which is delta G, equilibrium, we can't live without, and we'll also tie it into some thermodynamic values you talked about in Chem 50, which is delta H, which is our enthalpy. And we've seen it before as well. A reminder again, delta H, which is enthalpy or the heat of a reaction. And a lot of times, depending on the sort of sign of delta H, it'll tell us what's happening in the reaction. Is it endothermic or exothermic? So again, a negative delta H means it's a exothermic sort of process. Energy is released. Delta H is positive, is an endothermic process, which means energy is absorbed. And we'll definitely see our delta H come into play here with really both of these things. And it can have an effect on some of the thermodynamic sort of properties we're going to kind of talk about again in this sort of chapter here. So let's get into it, I think. So one of the things that we talk about in thermodynamics is the idea of spontaneous and whether or not a reaction is spontaneous. And sometimes people have sort of a misunderstanding of in the context of spontaneous here in a thermodynamic sort of setting of what it means. So sometimes we think about spontaneous and we think about like it's going to happen like really fast, and that's like spontaneous. And that's really not what we're talking about here in this sort of reaction or this sort of topic here. And spontaneous or a reaction is sort of favored to occur are going to be spontaneous. It has really nothing to do with how fast or slow a reaction sort of takes place. That is obviously the kinetics of it, as we talked about at the beginning of the semester. It is about really just whether or not that reaction will take place. And under those conditions, is it favorable for that reaction to actually take place? Be it really fast, be it somewhat fast, be it super slow. Are the conditions there for basically that reaction just to occur without any type of outside intervention to help it occur? And that is really what we're talking about when we talk about a reaction, for example, again, being spontaneous. Again, it has really nothing to do with how fast or slow. You could have, again, a spontaneous reaction that's really fast. You could have one that's really, really slow. But again, it's more so the idea of under those sort of specified conditions, will a reaction sort of happen? These are some spontaneous physical and chemical processes. Water runs downhill. If we take a lump of sugar, it will dissolve. Water will freeze below 0 degrees and melt above 0 degrees. Heat always sort of flows, as hopefully you know, right from the hotter object to the colder object. So the warmer object kind of cools down, the colder object sort of warms back up. Iron exposed to oxygen and water will form rust. So obviously, if you are skiing downhill, that most likely is going to be a spontaneous process. Pretty much you just need to get started and it's going to happen, right? And so forth. Obviously, if you're going uphill, that's a little non-spontaneous process. You can't sit at the bottom of the mountain, just magically, hopefully get up to the top, right? You got to put in some work, some energy to do that. And probably if you're coming down the hill, you probably don't want to see the person coming up the hill, I suppose, on the same mountain would probably not be a good thing. So again, spontaneous here has to do with the idea of just under those conditions, should we expect a reaction to occur? Again, it really has nothing to do with how fast or slow it does occur or does not occur, I guess, if it's non-spontaneous. Same idea here. This is a spontaneous sort of process. If we have all of our gas molecules on one side here separated by a valve, if we open it up, it's going to just spontaneously, right? They're going to kind of migrate over to the other side, and we will get some gas molecules going over there. Opposite here is true if we started with thinking with obviously gas molecules on both sides. They are not going to just magically just all decide, hey, let's just go over here on vacation. You would probably maybe have to help them over there, maybe, and kind of get them to the other side. Has to do some type of intervention there to try to get everybody back over to the other side. So when we talk about enthalpy, which again is delta H, does a decrease in enthalpy mean that the reaction will proceed spontaneously? So these are all, again, some examples of some spontaneous reactions. We have some combustion reaction here with methane. We have negative delta H, which means exothermic. Little acid base water formation here, also negative. So these are two exothermic type of processes. We have basically ice melting to liquid water. That's actually a positive sort of process. And dissolving a ionic solid in a water, also giving us a positive delta H sort of value. We know, for example, if you take an ice cube out, it's going to start to melt, right? You really don't have to do too much to it, again, because of the heat flow that's happening in that case, as the room temperature is hotter than the temperature of the ice, and the energy is going to flow from the hot air into the ice cube by itself and cause it to start to melt in that process. So one of the things that is helpful in a reaction, perhaps being spontaneous, is if it is exothermic. But as you can see here, it is possible definitely to have some endothermic reactions that are also spontaneous as well. So exothermicity does favor uh, a spontaneous reaction. It doesn't necessarily guarantee it. So we do have to look at another value to help us sort of understand whether or not a reaction will take place. And that other sort of value here is delta S and our entropy. Delta S is the change in entropy. And just spit that out. The change in entropy. There we go. So again, delta S is our change in entropy. And entropy is the measure of the randomness or disorder there is in a system. And remember that for a lot, when we talk about sort of a thermodynamic sort of information, oftentimes there is a system, which is pretty much whatever you're interested in. So that could be your beaker, it could be your test tube in the case of a lab. And then there obviously is the surroundings, right? Which is basically everything outside of whatever you're dealing with. So if your beaker was your system, then everything outside of it, it's your surroundings. So when we talk about entropy, it does deal with disorder. And as the disorder increases, the change in entropy actually gets more positive. So the more disorder you have, the more positive of an entropy value you will have. The more order you have, the more negative of a value you will have for entropy. So one of the ways we could calculate the change in entropy is to take our final state minus our initial state. A lot of these things are, if you remember as well, like state functions, and state functions only are important where you start and where you end. So if the amount of disorder increases, our S will become really more positive. So the delta S does become more positive, which is sometimes hard for people to kind of grasp because we kind of think of negative exothermic as negative kind of doing something. But here, actually, the more disorder you have, the more positive number will be, and more negative it will be, the more order you have. So whichever way you want to kind of think about entropy, be it order or disorder, you may always want to stick with one of them. Either the disorder is increasing, or the disorder is decreasing, or the order is increasing, or the order is decreasing. Probably one of the easiest things to sort of see that is with changes of state. Obviously, in a solid situation, everybody is pretty packed in there, tight to each other, pretty organized. And in the solid state, we would have a lot more order, a lot less disorder, and again would have more of a negative sort of entropy versus a liquid phase where they're still fairly organized, but there is definitely a lot more energy, a little bit more movement happening, so a little bit more disorder sort of happening there in the liquid state than we have in the solid state. And lastly, in the gas state, there is pretty much no order. We got all these things flying around and moving around with a lot of energy. That's going to create a lot of disorder, and it would have our greatest amount of entropy in gas. So gas is definitely more entropy, more disorder than you would see in solid. So if we take a look at just this sort of idea of ice melting, we are going from a more ordered situation to a more disordered situation. And that means that actually our delta S here will be more of a positive value in this case. Will actually become more positive because of that. Question. So the change in entropy is something that we can kind of help us use to figure out whether or not a reaction is going to be spontaneous, but not necessarily delta S just by itself. And we're going to talk about how we can use that here in a second. But before we get there, a little bit about disorder. Disorder is related to probability, and a probable event is one that can happen in many ways, right? An improbable event is one where there's only basically one or very few ways to sort of accomplish that. A ordered state has a low probability of occurring and a small entropy. Again, to get everybody sort of, if you want to think about lined up nice and ordered, right? There's kind of only one way-ish to kind of do that. Get everybody nice and organized. To get everybody all over the place, there's many ways people can kind of go all over the place. So if you think about everybody lining up for a big picture, right? There's one way to kind of squeeze everybody together. But if you want to take that picture, everybody just kind of goes their own way. There's a lot of disorder sort of happening and many ways to do that. Now, we can relate probability to what is referred to as microstates, and microstates are really sort of different ways that you can accomplish something. And microstates are sometimes referred to as W. And when we look at, say, for example, we wanted to put, 3 balls here into one side or the other. We're at the carnival, right? So if you want to win the big prize, right, and you got to get all 4 of those balls basically into one side. There's really one way to do that. In reality, you could go left or right, but we'll just call it one way in this case. Now, let's just say, well, maybe if you get 3 on the one side and 1 on the other, you'll get maybe a smaller prize. And there are 4 different sort of ways that you can accomplish that. And if you want just the participation prize there, you can get 2 on each side. There are 6 different ways that you can basically achieve that. So, with that being said, the higher the ways that you can achieve something, we're going to have more disorder sort of to happen here, right? So, and we'll have a larger delta S as opposed to our one way of doing something. This is what's sometimes referred to as the Boltzmann equation. K is the Boltzmann constant, which is down here. But if we just look at it, for example, here for our W that's equal to 1, if we did it here, natural log 1 is 0, right? So we will basically have an entropy of 0 or a small entropy, a more ordered event. If we were to kind of pop that one where there are many ways to sort of achieve it, that would be like the natural log of 6 there. And taking the constant out of that, that would get us like 1.79, which is obviously a much more positive entropy in that situation. So as W increases, we do get a larger entropy, more ways to do it. More ways to screw up than to do it right, right? So, there's only a few ways to do something right, and there's lots of ways you can screw something up, right? So there's a lot of disorder that happens and can happen in situations. Any questions on that there? So, taking a look at this, these are all processes where we do see an increase in the entropy, obviously, changes of states. So, solids are fairly ordered. Then we go to liquids, which obviously has a lot more disorder. Liquids out to our gas, which are flying around. The process of basically making a solution definitely increases the disorder before you dissolve it, right? There's two parts to our solution, a solvent and a solute. Before you do that, the solvent is organized and bound to each other, like all the water molecules are nicely organized and sort of bound to each other. So is our ionic solid, right? It's in an ionic solid where all of our ions are nicely organized and nice repeatable sort of patterns. Obviously, when we do that, we're breaking apart our nicely organized solid, our water, for example, sort of organization, and basically now we got ions floating around with water molecules or something like that surrounding each other. And obviously a lot more disorder over here. When we increase the temperature, we definitely will see an increase in the entropy. It's like lighting a fire underneath somebody. They're going to start moving around faster, right? Things are going to move faster. There's going to be a lot more movement than there would be at a lower temperature where there's less energy and things are not moving around as fast, if you will, and a lot less disorder happening at the lower temperature. All right, so take a moment for each of these and decide, how does the entropy of the system change for the following? Does the entropy sort of increase, decrease? Should the delta S be positive? All right, so let's take a look. Condensating water vapor. So condensation is going from gas back to liquid. So obviously in the gas phase, we have a lot more disorder, everybody flying around, to the liquid stage where they're not so much flying around. So we're definitely increasing the order, decreasing the disorder in this case. So we should see a drop in the entropy, and our delta S should become more negative in this case. Forming a sucrose crystal from a supersaturated solution. Crystals are essentially solids, right? So that definitely is going to be becoming more ordered again. Again, should decrease the disorder, and we should see a decrease in the entropy. And again, it should become more negative in this case. Heating hydrogen gas from 60 to 80, we're definitely increasing the temperature, which is going to cause our hydrogen molecules to start flying around a lot faster, cause a lot more disorder as they have a lot more energy. So we definitely are going to be decreasing the order here. We're increasing the disorder, increasing the entropy, and our delta S here should be a positive value. Question on those there. Last case here, sublimation. Sublimation is where we go from solid directly to gas, skip the liquid cleanup. So clearly here we're going from more order here to more disorder here. And that would then mean that we should see our delta S become more positive as we have a lot more disorder happening in this case. Any questions on those there? All right, so let's talk a little bit more about entropy. As I mentioned before, entropy is a state function. And as you may be familiar with state functions, things like energy, enthalpy, pressure, volume, temperature are state functions. State functions, again, really, there's only two important things, and that is sort of where you start and where you end. So, for example, if we look at these hikers and their potential energy, they both started down here, they both ended over here. The red guy took the scenic route around the mountain. The blue one took the more direct route up the mountain. They both really have the same potential energy at this point because they started at the bottom, ended at the top. And that is the only kind of important things. That's why when we calculate a lot of things like change in temperature, we take our final minus our initial. We do change in enthalpy as the enthalpy of our products minus the enthalpy of our reactants. And that is because in a chemical reaction, right, we have our reactants that go to our products. And in a chemical reaction, our reactants are our initial, right? And really our final state here are our products. So that's why, for example, when you calculate delta H, you go and add up all the product delta H's, you minus them from all the reactant delta H's, basically final minus initial sort of conditions. Now, one of the things you may remember when you look up delta H values, a couple of things, they typically are in kilojoules per mole, or kilojoules are the units that you typically find. You also typically find positive and negative numbers when you go to like a delta H table. You also should always make sure that you look up values right in the correct state. So if it's a solid, a liquid, a aqueous, you want to make sure you get it in the correct sort of state. One of the things that you may also remember is delta H values are pretty much zero for anything that is in their standard state uncombined by themselves. So things like H2O2, the way they naturally come, those guys typically have values of zero when you go to that table. Now, delta S, when you go to a delta S table, it is a little bit different, some of the things. The first thing that's a really major difference is all the values are positive values. So they'll all be positive values when you go to this table. And this is from your book, I think, this table. And the other really kind of important thing is the units are actually joules. So joules are typically the units that we associate with delta S, as opposed to delta H, where it is, as you can see here, kilojoules. Now, alone, it doesn't really matter too much, but we definitely will see some formulas where we use both of those values, the H and the S together. So you do want to make sure unit-wise at those points that you do a conversion. You got to either convert your joules to kilojoules or your kilojoules to joules so that all the units cancel out and you're not out by that factor of 1,000. So that's a very common sort of error we sort of get when we start using kind of both of those values together in formulas. Is those kind of difference in units that you find. Other thing that's also difference is you will actually, as you can see here in this table, you will find some values for things that you will not find values for delta H. So you will find values for things like H2O2. They are not zero for our entropy values. So these are absolute entropy values, and we actually have values for everything kind of else. Now, the first law of thermodynamics, as you may be familiar with, is really kind of all that delta H stuff, the law of conservation of energy. Energy is not created nor destroyed. All that stuff you probably did there in 50. That's kind of your delta H guy. And the second law of thermodynamics that we're going to talk about here a little bit is the entropy of the universe increases in a spontaneous process and remains unchanged in an equilibrium process. So what we use to help us decide whether or not a reaction is going to be spontaneous is actually what is on the bottom there, which is the delta S of the universe. So we do look at the delta S of the universe, and that's composed of two things: the delta S of the system, which a lot of times is your reaction, plus the delta S of your surroundings. And if you add those together, the system and the surroundings for the delta S, and you do hit a positive number for the delta S of the universe, then that reaction as it's written would be spontaneous, which once again does not mean that it occurs super fast or anything like that. It just means that under those conditions, you would expect that reaction basically to occur without any outside interference or help to make it occur. You have pretty much everything you need just to leave it alone and let it do its thing. Again, that could be really fast or it could be really, really slow. And that's what that means. Obviously, the opposite is true. If you end up with a delta S of the universe that's negative, then a non-spontaneous process is what you're looking at. And if you calculate the delta S of the universe and it equals 0, then you are at an equilibrium process, right? And things remain unchanged. In an equilibrium process, that is where we talk about the rate of the forward and reverse basically equal each other. There is kind of no net change happening on either side, and everything's going to basically maintain where it's at, and it would be an equilibrium sort of situation. So let's talk about how we calculate each of these. The first thing is the system or the reaction, and we calculate the delta S of the reaction by basically just taking our products minus our reactants. You basically go to the table, look up the values, do your products minus your reactants, and again, that's going to give you your delta S of the reaction, and that's going to give you your kind of final minus initial situation. Much like you might remember that you do with delta H, you do have to take the coefficients into account in the balanced equation. So when you look up those values, and let's just say there is, for A, B, and C, and D, and A is 50, you would have to multiply that 50 value by the coefficient that's in front of it, whatever that A may be, to get the proper value of it. So we do have to take the coefficients into account, and we could calculate our delta S of our reaction. As you may know or may not know, that little knot there usually means under standard conditions, and that usually means it's kind of like table values. You get them out of like a table, and for the most part, that is 1 molar if you're talking about concentration, and 1 atmosphere, or kind of like 1 bar if you're talking about pressure. Sometimes people will throw 25 degrees Celsius in there. Technically, it's not standard conditions, but most tables are done at 25 degrees Celsius, and that is typically where you find those things. So that's typically what you would do here. So why don't you give it a go here and calculate our delta S for this. I feel like one's missing there. CO2. Do I have that? Maybe on that other slide. Some chance. There it is. We'll go 213.8. Obviously, if they are not provided for you, you go find a table in the back of your book there where you'll probably find H values, S values, and G values together in a thermodynamic table. We're going to do our products minus our reactants here. So our delta S here going to be our product, which is 2 times our value of CO2, 213.8 joules. We're going to then subtract it from our reactants. So we'll go 2 times the value of CO, which is 197.9. We're going to add it to our other reactant, which is O2, which will not be 0 here, as we do have a value for it. Kind of put a big thing that way. And that's going to get us here. It looks like a minus 173.2 joules in this case. First off, any questions on the calculation? This does not tell us if this reaction is spontaneous or not. It just simply tells us what is happening with the order or disorder here. What is happening in this case? Is it increasing the disorder or decreasing it? The amount of disorder is actually decreasing, right? The amount of order here is increasing as we have a negative value in this case for our delta S. By the way, this is something that we could have predicted by just looking at the reaction. If I look at the reaction here before even doing a calculation, I have 2 gas molecules there and 1 more. That is a total of 3 gas molecules. On my product side, I am ending up with 2 gas molecules. I'm going from 3 crazy things flying around to only 2 things, right? So again, I'm going from a lot more disorder and things flying around to less things flying around and a lot more order. So we would predict, even before doing the calculation, that the reaction here is increasing the order, and we should end up with a negative value for our delta S for the reaction. Any questions on that? So a lot of times in the thermodynamic chapter, they oftentimes will ask you to do some of these type of questions where they may not even give you numbers. They'll just go, hey, this is positive, this is negative, or look at the reaction and make these sort of predictions. So it's very common type of question. All right. So as I just did there at the end, you can make a fairly good prediction without necessarily even doing the calculation whether or not you're sort of increasing or decreasing the order. So again, if a reaction actually produces more gas molecules than it started with, then you now have more things flying around than it started with, and that's going to obviously be a lot more disorder. I sort of think about like how many things are flying around my face, right? So you got a bunch of stuff flying around, a lot of disorder, not so many things flying around, a lot less uh, disorder happening. If the total number of gas molecules diminishes like it did in that example, we would expect a more negative delta S. If there's really no net change in terms of gas molecules, then you could have either one. It could kind of be positive or negative, but it would probably give you a small delta S value. So if we had to predict the sign here of this reaction, the delta S here should be positive or negative. What do we think here? It should be negative, as in this case, we started with one gas molecule. That's a solid, and that's a solid, no gas molecules, right? So we definitely went from something flying around to nothing flying around, right? So definitely a lot more order, a lot less disorder happening here. And that should decrease the entropy and end up with a negative value for delta S. Questions on that there? So that is how we calculate for our system. Remember, the other part of sort of the delta S of the universe is the surroundings. So we could see how the surroundings entropy is affected by certain things. And really, the two types of processes that we sort of undersee or undergo here is a exothermic process, and that is when again heat and energy is going to be released. So if we have an exothermic process that's releasing heat and energy to the surroundings, that means that the energy is going to be picked up by the surroundings, and all the molecules in the surroundings are going to gain a lot more energy. That's going to cause a lot more disorder in the surroundings as they pick up energy and start having more energy, start moving around and doing things. And we would see for the surroundings a more positive value for the change in entropy. Opposite is a little bit true here as well. In an endothermic process, that system's got to pick up the heat and energy from the surroundings. And when it does so, that means the surroundings will now have less heat and energy. And that's just going to kind of slow everybody down in the surroundings and can create a lot more order that's going to happen in that situation. And we would expect the delta S of the surroundings in that case to be negative. Basically, the delta S of the surroundings is proportional, that's what that little symbol is supposed to be, to negative delta H of the system. So if we just kind of map that out here, our delta H of the reaction and our delta S of our surroundings, which is negative delta H of the reaction, basically. So if we have a exothermic reaction, our delta H should be negative. Negative and negative equals a positive outcome for our surroundings. If we have a endothermic process, our delta H would be positive, and a negative and positive will end up with a negative outcome here for our surroundings. So again, the delta H here plays a role in the entropy of the surroundings, which is a part of the entropy of the universe that helps us determine whether or not, for example, a reaction is spontaneous. Any questions on that relationship? Now, does the temperature of the surroundings play a role in whether or not you'll kind of see a big change in the entropy? So let's just say, for example, here we had this guy and the surrounding temperature was really high. Would the amount of heat coming from the reaction make that big of a difference? And the answer is no, it won't, right? So if they're already crazy there in the surroundings, a little bit more crazy ain't gonna make a big difference, right? There's still gonna be crazy there in the surroundings, right? And a lot of disorder sort of happening. So for example, if you lit a match in just regular room, right, you could feel the heat coming off the match. Not that you should do this, but if you lit that match and put it into an oven that's been on at 550 degrees, that heat coming off of the little match there is not going to make a big difference in the energy there of the oven that's already at 550 degrees, right? So don't do that, obviously, or anything like that. But again, that's the idea there. So when we talk about surroundings, the change in the entropy for a given amount of heat absorbed depends on the temperature. Again, as I mentioned before, if the temperature is relatively high, that sort of added energy from an exothermic reaction probably won't make all that much difference. Um, or if the temperature of the surroundings is low, you are going to see a bigger difference. So how do we calculate the delta S of the surroundings? Kind of got all messed up there. I rewrite it. So the delta S of the surroundings is equal to minus delta H of the reaction divided by the temperature. Temperature here does need to be in Kelvin. Yeah, the temperature does need to be in Kelvin there. And again, we have our sort of opposite relationship here with a negative. So this formula here does have a negative value with it, and I mention it because later on in this chapter, we will see pretty much this exact same sort of formula, but there will not be a negative there. So again, the negative is there in this case to give us that opposite relationship between the system and the surroundings. Later on, it is not there because we're not really doing this relationship and it's not necessary. So it's sometimes very common people put the negative places where they don't. All right, so delta S of the universe is equal to our delta S of our reaction or our system. And that is again our delta S of our products minus the delta S of our reactants, plus the delta S of our surroundings, which is basically minus delta H over T. And again, that is with the two components that we could use to determine whether or not a reaction is spontaneous in this case. So let's take a look at one here and see what we come up with. So calculate the delta S of the system and the surroundings for the synthesis of ammonia. And is this reaction going to be spontaneous at 25 degrees Celsius? There's some values on the bottom that might be helpful. So why don't you take a few moments there and calculate. Okay, let's take a look. So really to know whether or not this reaction is going to be spontaneous, we do want to calculate the delta S of our universe, which again is our delta S of our system, plus the delta S of our surroundings. And we're looking for really a kind of positive outcome for that in order for it to be spontaneous. So we could calculate both of these components. We'll start with the delta S of our system, which is our surroundings. I'm sorry, which is our reaction. And we're going to take our products here. So we do need to go 2 times the value of NH3 because of the coefficient, 193 minus here we have a coefficient of 1, so basically just our N2 value there, 192, plus our coefficient of 3 here times the H2 value of 131 here, and that's going to give us our delta S of our system, which looks like it will be like a negative 199 joules in this case. Yeah. Any questions on that there? Once again, that number alone does not tell us if this reaction is spontaneous or not. This again will just tell us about the reaction itself. And because we have a negative value here, we are increasing the order, which we could have again predicted based on looking at the equation. That is 4 gas molecules going to 2 gas molecules. So instead of 4 things flying around with a lot of that disorder, we're down to just 2 things. So we're definitely increasing the order and could have predicted here again a negative value for our system. Questions on that there? All right, so now to the surroundings. Delta S of our surroundings going to be minus delta H over T. Our T here does need to be converted into Kelvin, so that's a 298 Kelvin. And here's our delta H here. So that is going to give me a negative 92.6. I'm going to multiply this by 1,000. And the reason I'm doing that is I know I'm going to need to add it to this number. So I'm just going to put everybody into joules. So that way everybody's in the right units. That way when I get to the adding part, I'm not adding joules and kilojoules, which is again a common error people do when they get to this part. So here I'm going to divide it by, what did I say there? 298. Looks good. And that's going to get me here a 92.6 times 1,000 to convert it to joules divided by a 298. This can give us a 311 joules in this case. Also makes sense if we think about it, right? This is a normal temperature. This is a exothermic reaction, which is releasing energy to the surroundings. That means the surroundings should pick up that energy and get a little bit more crazy, right? And that should increase the entropy of the surroundings. And we should expect a positive value, which we did get here in our calculation. So again, these are things you want to kind of think about as you're doing the calculations to make sure, you know, they do kind of make sense, especially with the signs, what they mean. So now we got that. They're both in joules because I made sure of it, which is good. And now we could just pop it into here, and we're going to go negative 199 joules plus a 311 joule. And that's going to get us there. We'll call it 112 joules in this case, yeah. Now, our delta S of the universe here is a positive value, which means this reaction should be spontaneous under these conditions. Once again, this is also a really good example of a reaction that is spontaneous, but super slow if you don't use a catalyst. So this reaction will take place if you let it be, but can be on the slow side if you're not using a catalyst to kind of help it along. Any questions on any of those sort of calculations there? Okay. So, as we talked about before, the third law of thermodynamics is the entropy of a perfect crystal substance is zero and at absolute zero temperature. So clearly, if you're making a perfect crystal, there should only be one way of doing that. And that would again give us our W that is equal to 1 and our entropy that is equal to 0. By the way, when we do phase changes, as we talked about, we are increasing the entropy as we go this way. So again, our delta S is becoming more positive as we roll through again our melting and boiling. This is kind of like almost like a heating curve, kind of upside down, if you will. But as you may remember as well, a couple of important sort of things with delta H as you go from solid to liquid or liquid back to solid. That does occur at the same temperature. That is typically the normal melting point, freezing point of a substance. And there's a certain amount of energy required just to do that transition. That is the delta H of fusion. Delta H of fusion is the energy required, again, basically just to take a substance from solid state to liquid or vice versa, liquid to solid. The temperature does not change because it happens exactly that. For example, for water, that's 0 degrees Celsius. At exactly 0 degrees Celsius, you have liquid water and ice crystals sort of happening. It's not until you get a little bit above 0 degrees that you transition to liquid water, not until a little below 0 degrees as you sort of fully transition to ice. But exactly there at 0 degrees, you have basically both phases in equilibrium with each other. And that's the delta H of fusion. So, for example, it's something like 6.01 kilojoules per mole for water at 0 degrees Celsius. And remember, as you go from solid to liquid, that is an endothermic process. So that is a positive delta H of fusion. The exact same number is needed to go the opposite way, liquid to solid, but it's exothermic in that case, so it would be negative. So in the case of water, it would be a positive 6.01 kilojoules per mole, or roughly 335 joules per gram. That is necessary to go from solid to liquid, positively put in there to like melt your ice cube. And if you were going from liquid water to ice and freezing it, it would be a negative 6.01 kilojoules per mole, or a negative 335 joules per gram. Same thing happens as you go from liquid to gas, or gas back to liquid. That is the delta H of vaporization that occurs. And that occurs at the normal boiling point of a substance. And same idea, exactly. The boiling point, you have both phases in equilibrium with each other, not till you get a little bit higher that you see the full transition. So for water, right, that's 100 degrees Celsius that occurs. Over here, this is 0 degrees Celsius. And at 100 degrees Celsius, it is something like 40.6 kilojoules per mole, give or take, depending on your book, or about 2260 joules per gram is the heat of vaporization for water. And it's the same idea. It is a positive number as you go from liquid to gas. It is a negative version of those numbers as you go from gas to liquid. As we will also see as we continue through this chapter, there is the entropy of fusion. And the entropy of fusion is the entropy change that occurs as you're transitioning from solid to liquid, or liquid to solid. And when we talk about the entropy of fusion, as you go from solid to liquid, it should be a positive number, and it should be a negative number heading in the other direction. And up here, we have the delta S of vaporization, or the entropy of vaporization. And that is the entropy change that occurs as you go from liquid to gas, and obviously backwards. Same idea here. As we go from liquid to gas, we're increasing the entropy. So it should end up as a positive value and a negative value rolling in the opposite direction, going from gas back to liquid, a more ordered state. Questions on that stuff there? Now, another thermodynamic value that is sometimes used to determine whether or not a reaction is spontaneous or not is actually Gibbs free energy. And Gibbs free energy is abbreviated with a delta G. Look at all these new letters here, delta G. And Gibbs free energy is pretty much what the title sounds like. It is energy available to do some type of work. So it is free to do some type of work. Not that it doesn't cost you anything, but it is available to basically do some type of work on a process. So as we saw earlier, we could use the delta S of the universe to help us determine whether or not a reaction is spontaneous or not. But for constant temperature processes, we can actually use Gibbs free energy to help us. And this is one of 5 different ways we'll use delta G. Maybe I'm exaggerating, maybe not. Minus T delta S. So we can actually use the delta G value directly to help us determine if a reaction is going to be spontaneous. So if you end up with a negative delta G, the reaction is spontaneous in the forward direction the way it is written. So the way the reaction is written in the equation, the reaction would occur from reactants to products. It would head towards the product side. If you calculate delta G and it's a positive value, then the reaction is going to be non-spontaneous as is written. It would actually become spontaneous if you reverse the reaction. And if you reverse the reaction, your reactants become your products become your reactants. And basically all you do is the sign changes, and it would go from a positive to a negative. So it would be a non-spontaneous reaction the way it's written. But if you did the reverse reaction, it actually would become spontaneous. And the delta G is equal to 0. It would be an equilibrium process. So this is one way that you can use delta G or calculate delta G. Delta G is equal to delta H minus T delta S. Again, with units, we want to be careful here, kilojoules for delta H and joules typically for our delta S. So once again, you do need to do a conversion. It is up to you which way you want to go, joules to kilojoules or kilojoules to joules. Temperature here, maybe not surprising either, it does need to be in Kelvin. Yeah, so we do need Kelvin here for our temperature. Now, my best piece of advice is to I would use the delta G equation that kind of fits the information that's given to you in the problem. So if you are given the delta H and delta S in the problem, this probably would be the one to use. Why reinvent the wheel? Just pop it into this equation and you could get your delta G value that you need. Um, so that is one way that we can, again, sort of solve for the delta G. Delta G, by the way, is typically given in kilojoules in terms of the answer. So typically delta G is similar to delta H, is usually given in kilojoules, with our delta S kind of being the odd one out there, is typically in joules. Now, another way that you could calculate the delta G is, frankly, you could do it like all the other thermodynamic sort of values. Delta H, products minus reactants, delta S, products minus reactants. You could also do delta G and take the products minus the reactants here. So you could calculate the delta G naught. That is sometimes referred to as the standard free energy of a reaction. And you basically will take the delta G is equal to our delta G of our products minus the delta G of our reactants. Just like we do with the other two, we do take the coefficient into account, so you do want to look it up. The standard free energy of formation, those are typically the values that you look up in a table. So when it says standard free energy of formation, that's kind of like your delta G value you can find in a table. And delta G is similar to delta H in the fact that, again, here you will have values of 0 for things in their standard state. Metals by themselves, H2, O2, those guys will have values of 0. So any delta G of formation will be 0 for an element that's by itself uncombined. Once again, that sort of standard not. These are typically what we talk about when we talk about standard conditions. 1 atmosphere for pressure if you're dealing with pure liquids, pure solids, and 1 molar in terms of our concentrations are usually our standard sort of conditions, our table conditions. So when should I use this one? Well, I would use this one if pretty much all you're given is the equation. You're asked to calculate the delta G, and that's all the information you're given. I would just go to the delta G table and do products minus reactants. Obviously, on the previous one, if I had an H or an S given to me, I would go into that equation rather than do this equation. Um, so why don't we try that there? There's some values there on the bottom that might be helpful. What is the standard free energy? Okay, so let's take a look. So obviously in this case, we're just given sort of the equation. We're looking for the standard free energy change. That's our delta G. If it was not given to you, obviously you would need to go look up those values in a table. So here we're going to do products minus reactants. So our delta G here going to be, for our product side, we got 12 times our CO2, which looks like negative 394.4. Plus 6 times our water there. We'll go with whatever's down there, negative 237.2. That takes care of all of our reactants. Then we'll do our product side. I'm sorry, all of our products. We'll do our reactant side. 2 times our C2 or C6, 124.5. And 15 times 0, basically, in this case. That's going to get us here 12 times negative 394.4 plus 6 times negative 237.2 minus basically 2 times 124.5. It's going to give us a negative 6405 kilojoules. First off, any questions on the calculation? Here, our delta G is negative. So since our delta G is negative, that means this reaction should be spontaneous. It means it should head basically towards the product side in this case. Questions on